part 2 of our little mini-series in programming a PIC microcontroller in assembler. Now, this is part of a larger journey, and on that larger journey, we're on episode 34 or something or rather, where we're building a digital lighting control system, and we have evolved to the point where we can start using a microcontroller. And today, we're going to dive into the assembly programming of that microcontroller. We're going to be controlling some digital outputs on the pins of that microcontroller. So basically sending highs and lows, or actually it kind of sounds like we're going to be blinking an LED. So yeah, it's not all that glamorous, but in the process of doing so, we're going to understand a significant amount of foundational understanding of how these microcontrollers work, because we're going to be playing with some of the timing and trying to get very precise and accurate control over it. So I'm excited. It's going to get a little mathy today, but I'm really excited about it. Now, what we're going to do is, since I did say this is part 2, Part 1 was the previous video, and that previous video laid the foundation of a PIC microcontroller. And if you haven't watched it, a lot of what we're going to do today might be a little bit confusing. So I highly recommend go back and watch the previous video before coming back here, because right now we're going to pick up exactly where we left off last time. And this is it. This is the assembly code program that we wrote on the last episode. We left this code in a state that it's ready to program. So let's do a quick review of what's in here right now. The first line organizes our code at the beginning of the program memory bank. In other words, address 000. The next line says go to initialize. Initialize is a label, and it refers to an address 0005, which is identified by this org command. So that means the next line starts at address 0005. And that line says clear F tris C. A quick peek in the datasheet shows us that tris C registers control the data direction. So by clearing it, we're making sure that port C is an output. And then the next line clears the latch of port C, making sure that all the outputs are 0. And in the main loop, we generate the complement of lat C and then branch back and do it all over again. So it takes the zeros and turns them into ones, and then turns them into zeros, and then turns them into ones. So we have this alternating signal of low and high on lat C. So the idea is, if we connect an LED to any pin on latch C, then that LED should turn on and off. And here is our breadboard with all the components that we plugged in on the last episode. Now, in addition to connecting the LED, there's a couple of other things we have to do as well. The datasheet tells us that any unused inputs and outputs can be configured as inputs and driven to a low state. We've done that with all of the outputs on port C. Alternatively, we can connect the pin to ground through a resistor. We're going to need to do that on all of the unused pins on port A because those are still configured as inputs, and we don't want to leave them floating. And we're using the 14-pin version of the PIC 16F213 microcontroller. On port A, we've already occupied pins 0, 1, and 3 for the programmer connections. Pin 1 and 0 are up here, and pin 3 is this one right over here. But that leaves pin 2, 4, and 5 open, so we're going to connect those to ground using a 10 kilo ohm resistor. These two make a lot of sense, but if you're wondering what's going on over here, this line over here is connected to ground through this reset switch. It was easier to do that rather than running a wire across the entire breadboard. Now we can attach our LED. This is just a regular low voltage indicator LED. I've chosen the color yellow or amber. Don't forget the resistor. In this case, we're using a 1 kilo ohm resistor, which is probably too high, but I want to make sure that the current coming out of this device is really, really low. And you probably noticed we connected the LED to pin 5 of port C. On our pin diagram, that's RC5 right over here. Now I'm going to connect the leads from our programmer. I won't worry too much about the programmer and how it works on this episode. We covered it a little bit on the previous episode, but honestly, it's a very involved topic about how to actually get that programmer to work, and I think I might cover that in a future episode. For now, let's just assume that it'll work. And the very next stage was to assemble this code into machine code. And we can do that by running our assembler. Now remember, this assembler is custom built. I wrote it, and so you may not be familiar with it, but that's besides the point. It does generate some output so we can see how this thing works. And in the assembler output, you can see the commands that we used, the addresses in which they live, and the encoded value, which is actually going to get programmed onto this microcontroller. And the next step was to program it, and here's the programming process. The important bit is right here with the program memory. The first row goes from address 0 to address F. The text on the right is everything that was encoded into our program, and you can see the first line of code here is 2801, which is the encoded value of goto, and that occurs at address 0. Then we have 4 blank spaces, and then 0194, which you can see here on the second line of code, which is the encoded version of clearf tris-c. The content on the left is what's in the program memory after the programming operation is completed. So we can see the code has been inserted into the right places, and everything else has 3FFF. And remember, 3FFF means empty. Great, now that it's programmed, this LED should be blinking. But it's not. That's because we haven't provided any clock source. The basic connection requirements in the datasheet identify there is a clock in pin when an external clock is used. There's also a set of internal clocks that we can use, but they need to be explicitly enabled, and we haven't enabled any of them. Lucky for me, we have an external clock source handy. The oscilloscope that I'm using has a handy calibration out feature that allows me to generate a square wave, and I can control the frequency of that wave right here through the software. And looking under the pin allocation tables in the datasheet for the 14-pin version, we can see that there is a clock in pin sitting on RA5. So let's plug in my external clock source into RA5. Taking another look at the pin diagram, we can see RA5 is this one right over here. And right now we've connected that to ground through this 10 kilo ohm resistor. So let's replace that with the clock signal. Did you see that? As soon as we plugged it in, the LED turned on. But wait a minute, our code didn't just turn the LED on, it's supposed to turn it on and off repeatedly. Let's use the oscilloscope, maybe that'll tell us something more. Aha, so it is indeed turning on and off. This signal clearly shows the low and high sequence we were expecting, but I'm probably sure you can guess as to why we don't see it on the LED. It's because that signal is inverting 833 times per second. That is way too fast for us to see on an LED. Let's also put our clock signal up on the scope to get more information. Look at that. Now that's nice. I think if we overlay the signals a little bit and then zoom in, now we can see that the yellow output signal inverts every 12 clock pulses, which means the main loop in our code takes 12 clock pulses to cycle through. And inside the main loop, there are 2 lines of code here, COMF and branch. In the instruction set summary, we can find the COMF instruction and note that it takes 1 cycle to run. We can also find the branch instruction and notice that it takes 2 cycles to run. So this makes it clear that the instruction cycle is not the same thing as a clock pulse. We have 12 clock pulses inside this loop, but only 3 instruction cycles. Well, that must mean that each instruction cycle takes 4 clock pulses. And indeed, that's exactly what it tells us in the datasheet. The instruction frequency is equal to the oscillator frequency divided by 4. The external clock frequency is 20 kilohertz, and as we just learned, the instruction frequency is our external clock frequency divided by 4. And while the frequency is important, the real key metric we're looking for is the period. In other words, how long does each clock pulse take? In order to figure out the period, we simply invert it, so it's 4 divided by the external frequency. In this case, it's 4 divided by 20 kilohertz, which delivers 0.2 milliseconds. So each instruction cycle takes 0.2 milliseconds. Now our main loop has 2 instructions, COMF and branch, and together they take 3 instruction cycles. So to calculate the main loop period, we can take the number of instructions and multiply it by our instruction period, which is 3 times 0.2 milliseconds. That gives us 0.6 milliseconds. So this controller will loop through that code every 0.6 milliseconds. Now to change the period back to a frequency, we just have to invert it again and multiply it by 2, because our code right now basically alternates between the low and the high signal. And we know based on this calculation that it will remain in either state for 0.6 milliseconds. But in order to figure out the frequency, we take that period and we multiply it by 2, because a cycle or a period is both the low and the high. It comes out to 1 over 1.2 milliseconds, which results in 833.3 hertz. And sure enough, 833 hertz. So the math works. But 833 hertz is still a bit too fast. We need to slow it down. To do that, we're going to need to do another calculation. Let's start with the same clock frequency of 20 kilohertz. We know that the instruction period for a 20 kilohertz clock is going to be 0.2 milliseconds. Below, I've identified our target frequency of 5 hertz. Now, based on that frequency of 5 hertz, we want to find out how long our main loop should take to cycle through. And I'm going to call that the main loop target period. And we can calculate that by inverting the frequency and then taking half of it. Because remember, each cycle of the up-down takes 2 loops, and we want to find out how long one of them takes. Plugging in our target frequency of 5 hertz, we can calculate the main loop target period to be 100 milliseconds. Now that we know how long the main loop needs to take, we can divide that by how long each instruction takes. Plugging in those numbers, 100 milliseconds divided by 0.2 milliseconds, results in 500 instructions. So that means our main loop needs to last 500 instructions. And right now, it lasts 3. So we need to induce a little bit of a delay here. And to introduce that delay, we're going to use a register from the general purpose RAM to hold a value that we will repeatedly decrement until we've used up 500 instructions. So the first thing we'll need to do is choose a register. And in the memory map, we can see that the general purpose registers start at address 020. So in our code, we can assign a label to that address of 020. And I'll put that in right at the front of our code underneath an appropriate comment. We start with the label name and then use the EQU directive? I have no idea if it's a directive, but whatever. EQU, and then tell it what address it belongs to. So now whenever we use that label in our code and assemble the program, our assembler will replace the label with whatever value we EQU it to. So we've created a variable. And just like any other programming language, when you create a variable, you have to assign it a value. And we're going to use the instruction MOVLW to do just that. We can find MOVLW in the instruction set summary right over here, and it translates to move literal to W. Now, from our last episode, we recognized that W is the working register or accumulator. We haven't used it until now, but basically it's a handy little holder that you're going to use all the time because a number of instructions reference the W or working register, and it basically allows you to put things in and process it and add stuff to it and move it away or subtract from it, all sorts of different things. All we want to do right now is assign it a value. And that's what this literal is. And based on this instruction, it uses an 8-bit value for K. So we're going to use this to assign our counter variable a value. Now, of course, right now we don't know what that value is, so we'll leave it blank. But this instruction simply puts that value into the working register. We now need to take that value from the working register and move it to our variable, which is located in GPR20. And that can be accomplished with the MOVWF instruction, which moves WREG, or the working register, to F. And remember, F is a target file register, and it's identified by this 7-bit value over here. We want to move the literal that we just placed into the working register into our variable GPR20. MOVWF GPR20. Now that we've moved this as of yet undetermined value into the counter, next we need to decrement that, or subtract 1 from it. In order to do that, we use the instruction DECF, or decrement F. Now this instruction has 2 parameters, F and D. We know that F refers to a target file register, and D from the previous episode refers to a direction bit. So a direction bit of 0 would indicate that the result of this instruction should be stored back in the working register. If the direction bit was 1, then that means that the result of this instruction should be stored in the target file register identified by F. And since we want to decrement the value and keep it in the variable, we're going to use 1 for our direction bit. Now we need to test the value to see if it's reached 0, because if it has, that means our counter has expired. If it hasn't, then we need to keep counting and decrement it again. So how do we test the value? For that, we use the status register. It's another one of those special registers that we'll use very often. The status register has a number of bits that will change depending on the status of the last instruction. The bit that we're interested in is this one, bit 2, or the 0 bit. Basically, what the 0 bit says is that if the last operation resulted in a 0, then this status bit will be a 1. If the last operation did not result in a 0, then this bit will be a 0. In our code, we decrement the value in our GPR20 variable, and we want to identify if that decrement has resulted in a 0. So we can test the 0 bit in the status to tell us that. And the instruction that we'll use is BTFSS, or bit test F skip if set. Basically, this instruction will test a specific bit in a given file register. And if that bit is set, in other words, if that bit is 1, then it will skip the next instruction. And this bit uses two parameters, the target file register and B, which is a 3-bit value. And as we know, 3-bit values can be anything from 0 to 7, which covers all of the bits in an 8-bit register. And so our instruction will look like this. BTFSS status, we want to test the file register status, comma 2, indicating we want to test bit number 2. And if indeed it is a 0, then we want to skip the next line. But if it's not a 0, whatever instruction we put in this next line will happen. And the instruction that we want in this line is to go back and decrement again. So we're going to use our familiar branch command to branch back to decrement GPR20. In this case, that is 2 lines up. And since we're going in the negative direction, we're using 1FD as our address. If you're confused about the 1FD, make sure you review the 2's complement topic that we talked about in the last episode. But basically, in this context, that 1FD means -2. And in the situation that that bit test does result in a 0, this branch instruction will be skipped and the COMF instruction will be run, which is exactly what we want. When the counter finishes counting, we want our output to be inverted. And then we need to adjust the branch offset in our next line of code to go right back to the beginning again. So we could calculate what value needs to go into branch, or we can use the label that already exists in our code. See, we already have a label for main. So rather than using the branch command, we can replace it with a simple goToMain, which will go right back to the beginning of the loop again. So this code is looking good, but clearly we're missing something. We need to define what value goes into our counter variable. Now we calculated earlier that we want to target a main loop delay of 500 instructions, but we can't simply put 500 in this counter because every instruction, as we've determined, takes time. And based on our previous calculations, I think it's 0.2 milliseconds per instruction. So we actually need to calculate how long this entire loop takes and then figure out what value to insert in there to know how long to count that loop. This is a little bit of a messy calculation, but let's get into it. I've written out our instructions on this sheet of paper. Beside each instruction, I've written how many cycles each instruction takes. In the datasheet, we see MOVLW takes 1 cycle. MOVWF also takes 1 cycle. Decrement F also takes 1 cycle. BTFSS says 1 and sometimes 2? Basically, if you look deeper into this, you'll discover that BTFSS takes 1 cycle every time it tests the bit. If the test comes back negative, then it just continues as normal. But if the test comes back positive, then it will take 2 cycles because it has to skip the next instruction. So in other words, the bit test F skip if set instruction will take 1 cycle every time except when it hits a 0, in which case it will take 2 cycles. So right now in our process, we'll assume that it takes 1 because this is the first time we're proceeding through the loop. And we'll make the assumption that the counter is greater than 1. And we already know that the branch instruction takes 2. Once our code reaches here, the branch instruction instructs it to go back a few lines. And we visualize that with this arrow over here pointing back to the decrement F instruction. I put a little x-1 in parentheses over there, and that defines how many times this code is going to loop. I'm using the letter x to represent the number of loops this will take. The reason it's x-1 is because we already know that the very last loop is going to be a little different because the BTFSS instruction in the last loop will take 2 cycles rather than 1. So we have an arrow that leads to another column of numbers that represents the instruction time for the final loop. The loop will always restart at the same instruction, decrement F, which we know will take 1 instruction. But then we reach the BTFSS instruction, And we know it will take 2 because this is the final loop and it will skip the next instruction, which is why the branch instruction has 0. It will go straight to COMF and then go to, and we know those are 1 instruction and 2 instructions respectively. Now with this diagram, I'm going to create an expression that we can use that'll help us figure out what the value of x needs to be. So I'll make the declaration that x equals the loop count, and I'm going to define another variable called n. So x being the loop counter is the number that we're searching for. This is the value that we're going to stick into our variable that represents our loop counter. But n is the number of times the entire main loop needs to cycle. Now we already know what the value of n is because we calculated earlier at 500. So let's work out that expression. Yeah, I know, it looks messy right now, but don't worry, I'm going to walk through it slowly. Basically, this expression is just adding up the numbers. So that 1 is this 1 here, and then we're adding another 1, and then we add another 1. But notice, I've started a parentheses here because the next series of numbers are inside the loop that we're already familiar with. So we have a 1, which is this decrement f, another 1, which is the BTFSS, and then the branch, which is 2. Now that whole bit is in the parentheses, and it gets triggered x minus 1 times. So I'm multiplying that by x minus 1. And then when the loops are finished, we go into our final stretch. So there's the 1 for the decrement f, then the 2 for the BTFSS, then the branch is 0, so that's the 0. Then we have a 1 here for COMF and 2 for GoTo. Then we can simplify that expression by bringing together some of the terms. So those 2, or this 1 plus 1 becomes a 2. 1 plus 1 plus 2 becomes 4. I'm going to leave the x1 as x1. 1 plus 2 plus 1 plus 2 equals 6. Simplify a little bit further. We can take this 2 and move it to this side, add them together to get the 8. So now we have 4 times x minus 1 plus 8. Simplify a little bit further. 4 times x minus 4. We basically work that part out, and then we add the 8, which leaves us with 4x plus 4. Now that expression, 4x plus 4, gives us n, or the number of instructions in the main loop. But we already know what n is because we calculated that earlier. Our target n is 500. So let's insert 500 into n and solve for x. We can bring that 4 over and subtract it from the 500, which leaves us with 496. Rearrange that a little bit and we get x equals 496 divided by 4, which equals 124. 124 in decimal equals 7c in hex. Now we simply enter that value into this MOVLW instruction. That algebra allowed us to develop an expression that gives us the number that we're going to use for our counter. And in this case, that number was 124, which turned into 7c, which should give us a frequency of 5 Hertz on the output. Let's give it a try. First, let's compile the code and then program. Aw, look at that. Our LED is blinking slow enough to see. And looking at the scope, sure enough, we see a nice 5 Hertz signal. But something looks a little odd about this signal. Every now and then, it seems to hold the low a little longer than it's supposed to. If I zoom out a little further, it actually looks like it holds that low every 2 seconds or so. What's happening here is that our device is actually resetting every 2 seconds. Why? Something called the Watchdog timer. This bad boy over here caused me a whole lot of headache. When I got started programming these devices, I spent days pulling my hair out. Yeah, over what was going on with this Watchdog timer. Although it was an incredible pain for me, this Watchdog timer is incredibly useful. The purpose it serves is to identify when something goes wrong in the code that you weren't expecting. Basically, it will reset the device at a regular interval unless you reset the timer. And the datasheet identifies that by default, all of the bits of the Watchdog timer control register are 0, which should equal an interval of 1 millisecond, which means every millisecond, this Watchdog timer needs to be reset. If it's not, then the Watchdog timer will reset the device. And when that happens, the Watchdog timer reverts to this reset value of a 2-second interval. And that's what we're seeing on the scope here, is that 2-second reset. I suspect it switches to 2 seconds because 2 seconds is slow enough for us mere humans to identify that something went wrong. Because if this thing was resetting every millisecond, it would appear as if nothing was happening, and I wouldn't know that anything was wrong to begin with. So to reset the Watchdog timer, we use this instruction called CLRWDT. And its purpose is obvious: clear Watchdog timer. So the solution is really that simple. We just need to insert this instruction so that it occurs at least every millisecond. And if we go back to our previous calculation, we know that each instruction lasts 0.2 milliseconds, meaning that 5 instructions will be processed in 1 millisecond. So our clear Watchdog timer cannot have more than 4 instructions pass before we call it again. So going back to the code, our first instruction is here, our second instruction is here, and then we get into our loop. So let's issue a clear Watchdog timer instruction before we get into our loop, and then issue it again just before the decrement and test, and then adjust the branch to include our new instruction. That way we can ensure that the Watchdog timer is cleared at least once a millisecond. Let's assemble this and write the program. Looking at our LED, it looks like it's blinking a little bit more steadily. And looking at our scope, we can see there are no more gaps in the signal, which suggests the device is no longer resetting. But the frequency's now changed to 4.008 Hertz. Well, that makes sense because we've added in a new instruction, and that new instruction takes time to run. According to the datasheet, the clear Watchdog timer instruction takes 1 cycle. So now we've introduced another cycle into our loop, but we haven't changed the loop counter. So in effect, our loop is now running longer, which has slowed down our frequency. Which means that this expression is no longer valid. We're going to have to recalculate this. So here's our revised code with the new clear Watchdog timer instruction. There's all the timings for the instructions. And here's a loop similar to what we had before, but this time it goes to the clear Watchdog timer instruction rather than the decrement F instruction. But it still must occur x minus 1 times. And the last time it goes through these timings. We're going to go through the same process and create the expression. The MOVLW is still 1 for MOVWF, and then we begin the parentheses, but note the parentheses is a little bit larger this time because we have the extra clear Watchdog timer instruction within the parentheses. So that's the extra 1 that's right over here. It still multiplies by x minus 1, and then it does the final bit just like it does before, except we have an additional 1 here for that clear Watchdog timer instruction. Simplifying that down, we result with 5x plus 4. Last time we had 4x plus 4. Just like last time, we'll set n to 500 and solve for x. And this time we get x equals 99.2. That 0.2 is a little bit of a problem because we have no way of entering a decimal value into these 8-bit registers. We need to deal with that 0.2, but there's a really clever way to do it. If you recognize that 0.2 is 1/5 of one loop, we can assume that that 0.2 is a single instruction. Because remember, this 5x refers to how many instructions are in one loop, and n refers to how many times we need to go through that loop. So the 0.2 is 1/5 of one loop, which equals 1 instruction. So all we need to do is add 1 more instruction, and we'll be able to bring this to an even 99. And the datasheet identifies the perfect instruction to use, a NOP, or no operation. Basically, waste 1 cycle, and that's exactly what we need. So if we insert a NOP between the branch and the COM-F, it will insert an additional instruction in this column right here, which will change this expression to 5x plus 5. Now we can follow the same procedure as last time. We let n equals 500 and solve for x. Bring the 5 over, 500 minus 5 equals 495, and then do a little rearranging, so x equals 495 over 5 equals 99. A nice round number that we can convert to hex and stick into our register. 99 decimal equals 63 in hex. So we'll simply change this 7c to 63. Let's save, assemble, and program. LED looks like it's blinking well, and looking at our scope, we have a perfect 5 Hertz signal. Now I'd like to identify an optimization that we can do to our code. It's a little one, but it's a one we'll use often. These two lines of code here, decrement F and BTFSS. As we know, this is to decrement the counter and test to see if it hits 0. Well, there's actually an instruction that does both of these in one. And that instruction is DECFSZ, or decrement F, skip if 0. You'll find this in many microcontrollers. There's often ways to optimize code by using less instructions to do the same thing. And those things are sometimes done so frequently that those instructions are baked right into the instruction set. So let's go right ahead and replace this decrement F with our new decrement FSZ. And then we can just remove the bit test instruction. Let's not forget to adjust the branch by 1. And we don't really need to assemble and test this because we already know what's going to happen. This messed up our timing again. And here's our revised timing diagram that we're getting awfully familiar with. So rather than bore you with the details, I'll just show you the end result. 4x plus 5 is our new expression. And working it out for an instruction target of 500, we get a resulting x of 123.75. Here's another decimal, but we can deal with this in a similar way than we did before. Recognize with our current expression we have 4 instructions in every loop, and 0.75 is, well, 3/4 of a loop, which means 3 instructions. So we could come in here and add 3 more NOPs, or we could remove the NOP that's there. And if we do that, our expression returns to 4x plus 4. Working through the target of 500 instructions, we end up with our result of 124, which I'm neatly displaying right over here. There's our expression, 4x plus 4, and solving for x, 124. In case we've forgotten, 124 equals 7c in hex. So in our code, we can remove this NOP line and replace the 6.3 with 7c. And if we assemble and program it, we get the 5 Hertz signal we're expecting. But what if we don't want 5 Hertz? What if we want to slow this down even more to 2 Hertz? Well, let's calculate that out. Our system clock frequency hasn't changed at 20 kilohertz, which means our instruction period is still 0.2 milliseconds, but now our target frequency is 2 Hertz. So working that out, our main loop target period is 250 milliseconds, and calculating for the instruction count, we end up with 1,250. Well, let's take our existing expression of 4x plus 4, but this time we'll let n equals 1250. And we'll work that out. We can take the 4, bring it over here, 1250 minus 4 equals 1246. And then rearranging for x equals 1246 over 4, we end up with x equals 311.5. Okay, so we already know how to deal with the 0.5, right? That's half a loop or 2 instructions. But that's not the important part. The important part is the bigger number, the 311. Even after we deal with the 0.5 and bring this down to 311, 311 in decimal turns into 137 in hex, which means it takes more than 8 bits to hold. Well, this is a problem because our registers are only 8 bits large. It cannot hold a value larger than 255. So 311 can't be held within a single 8-bit register, but it can be held in 2 8-bit registers or a 16-bit value, which means we'll need to assign another variable. This one we'll call GPR21 and we'll have it equal or EQU position 21 in our data memory. Referring back to our memory map, address 21 is well within this general purpose register bank of 80 bytes. But then we're going to have to add a few more lines of code to assign a value to the high byte. And let's adjust the comments and clear the value for the low byte because we haven't figured it out yet. And then we have to add another decrement instruction so that we can decrement the high byte counter, and then another branch that takes us back to the clear Watchdog timer line every time we loop in the high byte. Now for the hard part. We need to create the expression that'll allow for us to solve for 2 variables. We need the low byte and the high byte. And this is the timing diagram that's going to help us do that. All right, I'll do my best to walk through this. Here's our revised instructions, and I've added in another column just indicating which variable they are affecting. So the first two MOVLW and WFs are affecting the high byte, what we're calling Y. The next two MOVLW and WF commands affect the X variable. In our case, that's the low byte. We then have our clear watchdog timer and the decrement and branch for the X variable. Then we have a decrement and branch for the Y variable. And we can see here this branch goes back -2, which will take us back to the clear watchdog timer. And this branch takes us back -4, which also takes us back to the clear watchdog timer. And of course, we have our regular COMF and GoTo. And here's the timings for the first time we proceed through here. Nothing special about this, and we can come back using the loop identified here by x-1 for the first few loops. And then the final loop will take us back to this point, and then we proceed down into decrementing the Y variable. Now, after we've completed the first Y loop, I don't want to go back to here. Instead, I want to start a new column. The reason I want to start a new column is because the first time we go through this loop, we are setting both the Y and X variable. And then we loop the X variable sufficiently so that it expires down to 0. And then the Y variable will decrement once. Then we'll go back to start decrementing the X again. But this time the X has not been reset to its original value, which means it will be decremented from 0, which will bring it right back to 255. It goes all the way through. So the next few times that the X loop is cycled through, it's not going to use the value that we put into the X variable. Instead, it's going to go through all 256 counts for the entire X loop, if that made sense. So in the timing diagram, I'm illustrating that with the 256 minus 1. The last loop is still different, and it proceeds through the 1, 1, 2 timing. And then the last time it goes through that, it does the similar 1, 2, 0, just like it does over here. So in a sense, everything that's happening to the left of this line is the first loop of the Y variable. And then everything that happens within here is the subsequent loops of the Y variable, meaning not the first, not the last, everything in between. And because we're not dependent on an X variable for any subsequent loops, I'm just using static values, which we can actually calculate out, which I've done over here. I've said that this 1 plus 1 plus 2 is 4, so I have to loop 4 256 minus 1 times, which is 255, and then we add the 1, 2, 0 for the final loop. And that equates to the value of 1020 plus 3, or 1023. 1023 is the number of instructions that will get completed for every Y loop, excluding the first and last, which is why this loop says Y minus 2. The first loop is taken care of here. The last loop is taken care of here, or the final, but all the others, Y minus 2, are done here. And then we end off with the final loop, which starts off with the same value of 1023, and then we add the stuff outside the final loop, the 2 for the DECFSZ, 0 for branch because it gets skipped, 1 for COMF, and 1 for GoTo. Capturing all that data into an expression, we end up with the mess that we see here, and if you work out the math, you end up with n equals 4x plus 1026y minus 1018. I don't blame you if you didn't follow that at all. It took me forever to work through this, but it works. And so finally, we can take this target instruction count of 1250 and plug it into our new expression. But remember, we still have two variables to solve for, x and y. So to make this a little bit easier, we're going to ignore one of the variables. If you look at the expression, you'll notice that y has a much bigger impact than x. This 1026 is a lot bigger than 4. So we can temporarily ignore the x variable and set it to 0. We'll bring it back later, but for now, if we set x to 0 and work out the math, we end up with y equals 2.21. Now, in order to deal with the 0.21, we can round the y down to 2 and then enter the value of 2 in place of y and solve for x, which we've done here. I've entered in 2 for the value of y, and put the 4x back in, and then solved for x, which results in 54. So we entered in the value of 2, which in hexadecimal is still 2, into our high byte counter, and 54, which in hexadecimal is 36, into our low byte counter. Now we assemble and program, and oh, look at that. That's blinking a lot slower. Taking a look at our scope, a beautiful signal, precisely at 2 Hertz. All right, now we've done all of that with an external clock at 20 kilohertz. Earlier on, I mentioned that there are some internal clocks that we could use as well. How about we try using one of those? So there is a configuration utility in these devices which allow you to change the default value for the COSC or oscillator bits. And we can see by default, the external oscillator is operating. That's what we've been using so far. But if we change these bits to 1, 0, 0, 1, or 0, 0, we can select one of the internal oscillators, and there appear to be, well, 2. There is the low frequency internal oscillator and 2 settings for the high frequency. Let's take a closer look at the low frequency internal oscillator. The datasheet reveals more information about that low frequency internal oscillator. It says it's a 31 kilohertz oscillator. So in order to select the low frequency internal oscillator, we have to change the configuration bits of the device. Now, the method in which you change the bits is going to vary depending on the programmer that you are using. The programmer that we're using right now, as I mentioned before, is custom built. So it will recognize the commands that I insert into our code and translate that in the assembler to configure the bits. The method in which it does that is probably too complex for us to talk about now, and the method that you'll use if you're using a different programmer might be different. So hopefully it's not too different. So in my assembler, we just need to enter in some code. I'll create a section called config words, and I'll insert the first config word that I need to put in is rstosc equals 1. Going back to the data sheet, we can see rstosc right here in config 1. And the selection says if rstosc equals 0, 1, then we've chosen the low frequency internal oscillator. And that's what I'm doing right here by setting that value to 1. While I'm doing that, I'm also going to set the FEXTOSC to 1, which should disable the external oscillator. Going back to the datasheet, we can see it right here, FEXTOSC. If the value is 1, then the oscillator is not enabled. This, of course, is talking about the external oscillator. Now that's really all we need, but while we're at it, I'm going to add one more config word to ensure that the Watchdog timer stays enabled. The Watchdog timer configuration is actually in the next config word, config 2. Scrolling down, you'll find it right here, Watchdog timer enable. And we want to make sure that it's enabled regardless of sleep, and the value is WDTE, and I'd like to set that to 3. Remember, 1, 1 in binary equals 3 in hex. So in my code, I'll add one more config line, WDTE equals 3, to ensure that that Watchdog timer is enabled. Now, before we assemble and run this, we know full well that this will mess up our timing. So let's calculate and enter the new values for our X and Y variables before we assemble and program it. So to do these calculations, we'll start with a new clock frequency of 31 kilohertz. We can calculate the instruction period of 4 over 31 kilohertz, which gives us 0.129 milliseconds. The target frequency is still 2 hertz, which means that the main loop target period is still 250 milliseconds. Calculating the number of instructions that takes by taking the 250 milliseconds, dividing it by 0.129 gives us 1937.98. I'm going to round that to the nearest value of 1938. And then using our existing expression of 4x plus 1026y minus 1018, I'll simply insert 1938 and set x to 0, calculate y, which results in 2.88. I'll then round down to 2, insert the 2 in place of y, and then solve for x. Solving down, I get to 226. In our code, we already have 2 assigned for our y variable. we just need to assign the X variable at 226, which in hex is E2. Now we're ready to assemble and program. As we're repeatedly assembling and programming, you're certainly watching our program grow in instruction count and the amount of memory space it takes. Taking a look at our LED, we're still blinking at an appropriate rate, but our scope shows we're a little bit off. That's 2.03 Hertz. Not exactly 2, even though we did the calculations properly. Well, the datasheet gives us a hint as to what's going on here. That same page which told us that the internal low-frequency oscillator is at 31 kilohertz, it also says that the minimum is 26.5 and the maximum is 36. That's an awful big range, and it turns out that the low-frequency internal oscillator is just that way. It's inaccurate. If you want to use a more accurate internal oscillator, we must use the high-frequency internal oscillator. So let's use it. The configuration needs to be changed a little bit. The high-frequency internal oscillator with 1 MHz frequency needs us to set the RSTOSC word to 2. So let's make the change in our code. And as we expect, we got to redo the calculation for the higher speed. So our system clock is now 1 MHz, which makes our instruction period 4 microseconds. We still have a target frequency of 2 Hertz, but now our main loop target period is 250,000 microseconds. Notice I've switched from milliseconds to microseconds because, well, our clock speed is way higher now, so we have to work with tinier and tinier periods. Our main loop target instruction count is calculated by taking that main loop period of 250,000 microseconds and dividing by individual instruction of 4, which gives us 62,500. Working that through a calculated expression, we end up with values of 61 for Y and 233 for X. 61 in decimal is 3D in hexadecimal, so we'll change this 2 to 3D, and 233 in decimal is E9 in hex, so we'll change this E2 to E9. The other thing that we might want to recognize is this faster clock speed will reduce our need to clear the Watchdog timer so frequently. Remember when we originally put those clear Watchdog timer instructions in, we were thinking that you'd have to do it at least every 5 instructions. Well, now with the 1 MHz clock speed, you can go 250 instructions before we have to clear the Watchdog timer again. So technically, we could go in and remove one of our clear Watchdog timer instructions, but we know what that's going to do. It's going to change our expression, so I'm not going to bother doing that. Instead, I'm just going to assemble and program. Looking at our LED, we're still blinking at a reasonable rate. Confirming with the scope, we're still at 2 Hertz, a little bit over 2. Looks like it's 0.04 Hertz, but a lot closer than it was before. Remember, the internal oscillators are not going to be super precise. The only way to get super high precision is to use an external oscillator like we were doing earlier. There's one other configuration bit here that's interesting. The clock out enable bit is defaulted to 1, in which case the clock out function is disabled. We can turn it to 0, which would enable the clock out function. In other words, the device will output its internal clock onto one of the pins. The specific pin can be found in the pin allocation table. Here's the clock out pin. In this case, it's going to be RA4. And RA4 right now is occupied by this resistor. So that external clock input is not needed anymore. We can remove it and replace it with the 10 kilo ohm resistor. Then we could attach our scope to the clock out pin and take a look at the internal clock just to prove that this thing is actually running at 1 MHz. Then we add our config word to enable the clock out, assemble, and program. And of course, looking at the scope, we're not seeing much. That's because the clock is running very fast and our time base is very slow. So let's zoom in the time base quite a lot. And the clock is starting to come up here. And there we go. We can see channel 2 running at 250,000 kilohertz. Remember, we're looking at the instruction clock, not the system clock. And we already know that the system clock is 4 times the instruction clock. So 250,000 kilohertz times 4 is 1 megahertz. Well, it's running at 1 megahertz. And because of our wonderful timing algorithm, Our LED is still blinking at 2 Hertz. All right, so we did a lot of work today, and for not a lot of results. I mean, all we've really done is control the timing of a blinking LED, but we've done so and gained a powerful foundational knowledge of how this microcontroller really works, the intricate timing involved, and how every subtle change can change and completely throw off all the timing. All of that frustration, I think, was really helpful for me especially to get a good understanding of all the tweaks that we can do within this microcontroller to gain a high precision control over all that timing. Practically speaking, this is not how you blink an LED. There are much more efficient ways because with the code that we have right now, the processor or the controller is busy doing nothing but counting. That's all it's doing. It can't do anything else. There are much more efficient ways to count or keep time, I should say, and that is with these peripherals called timers. And we're going to cover those on the next episode, and they are used absolutely everywhere. So I am very much looking forward to the more efficient way of doing things. We'll get into that next time.